2.2 talks about limits involving infinity. So we talked about how limits are looking at characteristics of a function as it gets closer and closer to an x value. So these we're going to talk about what happens when the function is going towards positive or negative infinity when we get to that value. We're also going to talk about what happens if we're looking for limits as x gets closer to positive or negative infinity. Now, a couple of things that you need to realize. If we have a number line here, off to the left gives us negative infinity, and to the right is positive infinity. These are symbols that show us that we're getting further and further on down that line. They are not numbers. Infinity is not a number. It's just a symbol, a representation of how far out we're going. So keep that in mind. You can't have something that equals infinity. We'll kind of say that in our notation, but it's not really possible because infinity is not a number. So first let's look at the function f of x equals 1 over x. So we have it here in our graph. Now if we want to look at the limit as x goes to negative infinity of this function, if you look here, the graph gets closer and closer and closer to 0. And so that means our limit as x goes to negative infinity is 0. It doesn't actually get to 0, but remember, a limit is what does it approach as it gets there. Now, if we go to positive infinity, and you'll find that my limit symbol gets sloppier and sloppier, and sorry, hopefully you can tell what it is. If we get to positive infinity, again, the graph comes down, and as it goes further and further out, it's approaching 0. So the limit as you get to positive infinity is 0. Again, it never actually touches 0, but that's where it gets to. Now, how is this helpful? This is helpful because it gives us our horizontal asymptotes. Now remember, we talked about horizontal asymptotes some before, and we've pointed out that you can cross a horizontal asymptote, but a horizontal asymptote tells us towards end behavior. So if you have the limit as x goes to infinity of a function equals some number, then you have a horizontal asymptote of y equals that number. Or if you have the limit as x goes to negative infinity of that function equals that number, then you have a horizontal asymptote of y equals b as well. Okay, so the limit as x goes to infinity gives us those horizontal asymptotes. Now, let's look at a couple of graphs and see what happens with them. What if we have a function g of x equals 1 over x squared? Now, before we look at that on the calculator, let's talk about it a little bit. What do we know about it? Well, we know that it's going to have, it's going to always be positive. We know that it can't be equal to 0. Those are some things that it looks like. So let's come over here to our calculator, and let's leave 1 over x in there and then put in 1 over x squared so that we can compare the two to see what happens. Now, if you have different colors on yours, you might want to put them in different colors so you can make sure you can see it, but I don't know mine, so we'll just have it in black and white. All right, so 1 over x is this one and this one, and 1 over x squared is this piece here and this piece here. Okay, so if we want to figure out what the limit is as x goes to infinity of 1 over x squared, then we can look at the graph and see that it heads to 0. But I want to use this to illustrate the sandwich theorem as well. So I'm going to change my window so that we're looking out towards infinity as we get closer and closer out there. Let's say, let's go from 50 to There we go. And so we don't have all the little units, we'll just put it in 10. So let's get this, and it's going to graph this, and it's not close enough. Oh, my calculator thing is freaking out again. Alright, so we're going to put it back in a standard window. But let's see if we can get it so that it'll show up. Alright, so that's 1 over x, and that's 1 over x squared. I'm going to adjust. If it'll show it to you, there it is. Alright, so, and then I'm going to adjust my y's again, just so we can get an even better picture. That's 1 over x is the first one, and then 1 over x squared. So this coming here is 1 over x, and this here is 1 over x squared. Okay, obviously it's going to get small faster because when you square something, 1 over that's going to get smaller and smaller. So what we see here is as we get out towards infinity, we have 1 over x, that 0, which is the axis here, is smaller than or equal to 1 over x squared, which is smaller than or equal to 1 over x. And we can use that sandwich theorem. Because we know that the limit as x goes to infinity of 0 is just 0. And we know that the limit as x goes to infinity of 1 over x, we saw that in the first part of the video, is equal to 0. So that means that this is true. Now, obviously, you can look at your graph and see that it's going to be true. But I just wanted to show you one more example of the sandwich theorem because we did that so briefly yesterday, or the last time. We had video. Through the sums and the differences and the rationals and all that kind of stuff. You can use the sandwich theorem. So let's look at a couple of examples here so that we know what we're dealing with. So if we have the limit as x goes to infinity of 1 over 1 over x cubed plus 8. Well, if you have x greater than 0, which you do because you're going out towards infinity, if you have x greater than 0, then you know that one thing is true. We know that x cubed plus 8 is bigger than x. Is that true? Of course it's true. If you're going to cube something and then add 8 to it, it's going to be bigger than that something to start with. Well, how does that help us? Well, what that means is the reciprocal is going to be less than that reciprocal. Okay, think about that for a second. Make sure you understand why that's true. So what that tells us, we've got that, and we know that, of course, this is going to be bigger than 0 because we're talking about x bigger than 0 here. So again, we can use the sandwich theorem. So we know the limit as x goes to infinity of 0 is 0, and the limit as x goes to infinity of 1 over x is 0. So that means that this limit has to be 0 as well. Now, what are some other tricks to use to help you with this? Well, if we have the limit as x goes to infinity of a rational like this, because we know the 1 over x and the 1 over x squared limits already, we can figure this one out. Now this one, if we divide by x squared on both of them, whatever this biggest one is, we get the limit as x goes to infinity of 2 minus 2 over x plus 3 over x squared over 1 plus 4 over x plus 4 over x squared. Now, we can use all these rules, the quotient rules and sum and difference. So we're going to end up with the limit as x goes to infinity of 2 minus the limit as x goes to infinity of 2 over x plus the limit as x goes to infinity of 3 over x squared all over the limit as x goes to infinity of 1 plus the limit as x goes to infinity of 4 over x plus the limit as x goes to infinity of 4 over x squared. Now, do you have to write that all out every time? Of course not. You can just think it in your head and figure it out. Well, this one you know is going to go to 0, and this one to 0, and this one to 0, and this one to 0, because the limit as x goes to infinity of 1 over x and the limit as x goes to infinity of 1 over x squared are all 0. We saw that from our graphs. So what's the limit as x goes to infinity of 2? Well, it's just 2. And the limit as x goes to infinity of 1 is just 1. So our answer is just 2. Generally speaking, you divide by the highest power of x in the denominator, and then you can simplify it all out. One thing I want to point out, make sure you remember that infinity over infinity is undefined. So if you get, you're looking at the limit as x goes to infinity and you get x over x when you simplify it, or, well, if you get something that's going to go to infinity into infinity, it's going to be undefined if you have x over x. Now, there's some rules that you need to learn. You need to make sure you have down that will help you with these rational equations. So if we have a rational equation, and it's made up by a polynomial on the top and a polynomial on the bottom, and let's see, one is the degree of polynomial p of x is greater than the degree of polynomial, these have to be polynomials, so polynomial q of x. Then you have the limit as x goes to infinity of this rational function is equal to plus or minus infinity. Okay, now that's not really an answer. Technically speaking, that means the limit doesn't exist. But we'll put positive or negative infinity because that gives us an idea of their end behavior. If you have the degree of polynomial p of x is equal to the degree of q of x, then you have the limit as x goes to infinity of this rational equation, p of x over q of x, equals a ratio, cn over dn, where cn is the leading coefficient. Remember, that's the one with the highest degree term. Coefficient of p of x, and dn is the leading coefficient of q of x. Alright, so you just take a ratio of the leading coefficients if their degrees are equal. We just saw that in the last example we did. We ended up with a ratio of the leading coefficients because the degrees were equal. Now, if the degree of p of x is less than the degree of q of x, then the limit as x goes to infinity of p of x over q of x is equal to 0. So now you've got these 3 rules. You need to know these. These are something that you should put on your card for studying for your exam, in your little spiral bound of 3x5 cards, and something you definitely need to have in notes because it's not in your book. So make sure you've got it written down. This gives us horizontal asymptotes as well for these rational equations. Because remember, we said a horizontal asymptote is the limit as x goes to infinity of that function. So we can look at those and know that. Make sure you know these rules. Now, vertical asymptotes. Vertical asymptotes are a little bit different. So remember, a vertical line is x equals a number. We'll call that number a. So x equals a is a vertical asymptote if either the limit as x goes to a from the right of the function is positive or negative infinity, or the limit as x goes to a from the left is positive or negative infinity. So with horizontal asymptotes, we're looking at the limit as x goes to positive or negative infinity. For vertical asymptotes, we're looking at the limit as x goes to a number from the right or the left, and the result is that the function is going off towards infinity or negative infinity, either way. So for example, if you look at our graph here, if we go back and put it in a standard window, and it's going to freak out again. So if we have our equation y equals, let's just go with 1 over x. We'll just clear the other one. So for this one, if we look at as we go to x equals 0, so the limit as x goes to 0 from the right of 1 over x, if we're coming from the right, then we're going up and getting bigger and bigger and bigger and bigger. We're heading towards positive infinity, which means the limit doesn't exist. It's just going off into positive infinity. And if we go from the left, coming around from the left and go down, 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 we're going to negative infinity. This means that x equals 0 is a vertical asymptote for this function. Now we already knew that because that meant the bottom was going to be 0 and we couldn't simplify it and cancel it out so that it'd just be a hole. But this is the technical definition of vertical asymptotes, so make sure you know that. Now the other thing you need to look at is as we're looking at limits that we get to infinity, we're looking at end behavior. So sometimes we need end behavior models because the function we're looking at is really complicated, and we just want to see the model as we get towards infinity. Now, if you have a function, let's say we have f of x equals 3x to the 5th minus 3x cubed plus 17x plus 2. Now, if we want to look at the end behavior model for this, then what you look at is this first, for a polynomial, you're going to look at that degree giving term. And you can look at these graphs of this whole thing here and this one, and if you look way out in infinity on both sides, which I encourage you to do on your calculator, look out, at 100. How do they look like? What do they look like at x equals 100? They will be getting more and more similar. That means that this can be an end behavior model for this function here. Now, you can only use an end behavior model if the limit as x goes to positive or negative infinity of the function divided by that end behavior model equals 1. In other words, you have to have the same degree and coefficient. See if we set this up. The limit as x goes to infinity of 3x to the fifth minus 3x cubed plus 17x plus 2 over 3x to the fifth. Well, you can divide everything through by x to the fifth and use the way we did originally, or you can just look at those three rules I gave you, and you see that the degree is equal, so that means we're going to use the ratio of the leading coefficients and see that that equals 1. So go back over and make sure you understand why those three rules work, looking at the example we did before that, where we divided everything through. But the end behavior models, the biggest thing to realize is when you have a polynomial, the end behavior model is just that first term. And then if you find that you need other end behavior models for more complicated functions, you can look at the graph and see what does it look like and how does that work. Now, one thing I want to point out is sometimes the limit doesn't really exist. So let's say we have the limit as x goes to infinity of the cosine of x. Well, what happens as x goes to infinity of cosine x? Well, it's just going to keep going like this, right? Is it getting anywhere? Is it going to land near something? Is it approaching a value? No, it's bouncing between -1 and 1. The function value is bouncing between -1 and 1. So we don't have a limit. And that happens sometimes with your more complicated functions. So read over this section 2.2. Make sure you've got your questions written down and you've thought about this stuff thoroughly. Make sure you understand why these things work. And we'll talk about it some more in class.